Welcome to the first of our AC interference webinar series. What is AC interference and how does it affect your pipelines? Our panelists today are Andy Florence, Director of Integrity Management Services, and Clay Brailsford, President of Bass Engineering. Take it away, Andy.
Anna, thank you. And thank you to everyone who's taken the time out of their busy day and their busy schedule to spend an hour with us to talk about AC interference. AC interference is an interesting topic. It's been around it's a known phenomenon. It's been around for quite some time. So what we hope to answer for you in the next few webinar series in a few weeks is this really a problem that you need to be aware of? What can you do to mitigate? And where do you get started with your program? So again, it's a good time to be in the oil and gas industry, particularly in the pipeline industry. We're all very, very busy. I want to thank you for taking an hour out of your day to spend with Clay and I today. So over the next four sessions, actually the next month or so, we're going to cover 4 different sessions or 4 different topics, broken up into 4 parts. Today is AC interference 101. We're going to give you a definition of what AC interference is and what some of the things you can look for out in the field to see if you have an AC interference problem. We're also going to take a step back and look at it at the 50,000 foot level and see, do I really have an AC interference problem? What are some of the macro factors that are driving this problem into the pipeline industry? Session 2 will come back in 2 weeks. We've established the fact, hopefully, that you understand that you might have a problem with AC interference. So we're going to help you understand how to mitigate AC interference. And the analogy we'll be using throughout our presentation is that of a multi-headed monster, an elusive and dynamic monster that you're never going to kill, but you're going to be able to tame it and control it. So with our mitigation options, we'll give you some tools for your toolbox to help you control AC interference and keep that monster in its cage. 2 weeks after that, part 3, we'll come back and talk about AC threat assessment. Obviously, the best time to address AC interference is when you have the ditch open and you're in construction. If you know you're close to a power line, that's the best time to do your mitigation. But what about your legacy pipe? Suppose you have 7,000 miles of transmission and high pressure main lines that you installed many years ago, and AC interference wasn't a known problem, and the problem wasn't addressed at the time of construction. So you can't just ignore your legacy pipe. You need to understand what you can do to mitigate the threat to AC interference on that older pipe as well. So we'll give you some techniques and some ideas about how to jumpstart your AC interference threat assessment program. And then we'll come back 2 weeks after that in part 4, and we'll talk about some tools that you can do for monitoring AC interference in the field. Again, this multi-headed monster is elusive and dynamic. It's there one day and it's gone the next. So you can't just go out into the field, take a reading at one point in time. You need to monitor your assets and the exposure to this threat over time. So we'll offer up some tools at the end of the session to help you understand what you need to do to monitor AC threat. By the end of the 4 sessions, we hope to have answered all these questions. These are some of the key questions related to AC interference. Specifically, what are the causes? What are the characteristics of AC interference? If you're out on the right of way, what are you looking for? If you suspect you've got an AC problem, what do you need to look for while you're out there looking at the pipe? What do the regulators say? Both the feds and the state level governments, what do they tell you have to do with regards to AC interference? Your tax dollars at work will try to help you understand what the feds tell you have to do. All of our pipeline systems, metallic pipeline systems, are CP protected. So now I've got DC running along my pipeline. What does AC do to my CP system, my DC CP system out there? How does that impact my CP system? Am I exacerbating the problem, or am I actually mitigating 2 problems at one time? And how do I get started? We talked about that earlier. How do I get started assessing my legacy system for AC interference with the threat assessment? Give you some ideas and some tools about how to start addressing your older pipeline systems. AC interference is not just AC, not just induced AC on your pipelines, but it also can be a fault condition from a power line, nearby power lines as well. So what can lead to a fault damage, and what does that mean to my pipeline? And then there's also AC. Is AC interference really a threat to my personnel? Is it not just the damage to instrumentation in my pipeline, but what kind of exposure do the public and my own staff have if I'm co-located next to a power line? And then what can I do to mitigate AC interference? During the course of the presentation, the webinar series, if you guys have questions, you should see a button on your webinar controls there, your little dialog box there. Feel free to send us questions. We'll try to answer those questions at the end of the presentation. So, feel free to send us questions. We'd love to have that feedback. So let's start with the definition of AC interference. About 3 or 4 years ago, maybe 2 years ago, INGAA, which is the International Gas Association of America, Interstate Natural Gas Association of America, commissioned a study, and some poor engineers were tasked with to go out and read all of the documentation relative to AC interference and to bring it together into a concise document, one document that can give guidance to operators out there. And there's a lot of documentation out there around AC interference. Some of the earliest documentation that I've read goes back to the 80s. So it's a well-known phenomenon. It varies in verbosity and varies in clarity. It can be contradictory. So INGAA said we need to get this under control, and we need to read all this documentation and put it into a single report that's going to give some guidance to pipeline operators. And they came up with this definition of what is AC interference. And it's a good, succinct definition. But at the same time, it does have some technical terms in there that if you're not familiar with basic electrical engineering, you might not understand. So in layman's terms, what is AC interference? It is, if I were to talk to my mother and describe what it is basically if you're standing next to a power line, you look up and you see a power line, and you look down and you see a metallic object next to it, you can bet that there's a charge on that pipeline or on that metallic object that you better not touch, because it's charge is coming off of the overhead power line and is charging that metallic object. So it's an uncontrolled charge on this metallic object that poses a safety hazard to you. If you touch it, it could shock you, and it could give you enough shock that it could cause you some injury or even death. Also, it's an uncontrolled energy source, electrical charge on that metallic object, and if you don't control it, over time, that metallic object that's receiving that charge from that overhead power line is going to quickly degrade over time. You'll have accelerated corrosion up there. So I would recommend, if you haven't read this report from INGAA, that you download it and read it. It's about 80 pages long. It does a really good job of, again, giving a definition of AC interference, but at the same time, it gives you some clear guidance and some criteria over some leading indicators that would indicate that you have AC interference on your pipelines out there. Download that document. It's free on the internet out there, and take a read. Again, for a technical document, only 80 pages, it's well written. So we've defined AC interference. We know that it's existed for a long time. It's been around, documented, like I said, back into the 80s. But do I really have a problem in the larger space of pipelines out there? In other words, if I step back at 50,000 feet, is there a big enough problem? Has this problem evolved over time such that it warrants a webinar like this? Is this an industry-wide problem? So the first question that we asked was, back up. First question we asked was, well, let's take a look at the hazardous liquid pipelines in all of the United States. And that's what this map represents, the yellow lines here. These are hazardous liquid transmission pipelines in the United States. Not a terribly complex network of pipe. Makes a lot of sense, right? You got your plays out in the Permian Delaware Basin, taking pipelines or taking the products to Cushing for storage, down to the refineries in Houston. A lot of raw product coming out of Fort McMurray up in Canada down into the United States, then transporting it out to the West Coast as well. But not a real complex geometric network. So if I were to extrapolate that, I'd say not a lot of metal in the ground, not a lot of natural conductor in the ground. Now let's take a look at our natural gas pipelines. Gets a little bit more complex, gets a lot more metal in the ground. It also makes sense. When we're extracting gas out of our wellheads, we're separating and we're scrubbing and we're preparing that product before it gets into the trunk line, and then we take it directly to our consumers in the city gates out there. So I don't have to centralize transportation of this product into one location like the fineries or the storage locations of Cushing. I can take it directly to the city gates. So naturally, I have a much more complex network, and I have a lot more metal in the ground. So it's starting to look a little more crowded. Let's take a look now at the electrical transmission system in the United States. The blue here represents all the electrical power lines, transmission power lines in the U.S. And you can see, no surprise, East Coast, densely populated area, lots of electrical transmission lines out there bringing power to the consumers out there. As you move west, not so much, but we all know that our population is moving west. So over time, you would see electrical transmission lines just as dense as you would see on the East Coast or the West Coast as you would on the East Coast out there. So if I bring it all together, I've got my electrical transmission lines carrying a high charge up in the air. I got a lot of pipeline in the ground and natural conductors in the ground. If I bring it all together, it's a crowded environment. So it really is a problem that is continuing to exasperate itself and to become a larger and growing every day. As we put more pipe in the ground and more electrical transmission in the air, you're going to be running into AC interference more frequently. Next question we asked, well, that was as of today. What about tomorrow? We continue to invest in the pipeline industry. Pipeline Gas and Journal tells us that there's 9,500 miles of pipe under construction in the United States today. Another 26,000 miles in planning stages for the next 3 to 5 years. So a total of 36,000 total miles of pipe, new metal, going into the ground in the next 3 to 5 years. At the same time, our friends over in the electric company continue to invest in their infrastructure as well. You can see the chart on the left there. This is a breakdown of the different capital investments from electrical companies. You can see that they're continuing to invest in their station equipment, their overhead lines and devices, their towers and fixtures. So they're going to continue to put more cable in the air, more metal, charged metal in the air, and they're also going to be pushing more power through those conduits as well. Off to the right, you'll see where does that demand coming from? It's residential and commercial. By 2050, the United States Energy Information Agency predicts that residential alone will be demanding a little over, probably looks like about 1,800, 1,700 billion kilowatt hours. And the commercial groups will be demanding the same amount of power as well. So consumer demand and commercial demand for power can continue to grow. If I were a utility company too, I would continue to invest in my infrastructure as well. And I would continue to put more metal up in the air, charged metal up in the air. Finally, let's take a look at, well, all of these consumers, where they're going to be living. This prediction for this particular study shows that by 2045, 9 out of 10 Americans will be living in an urban setting. So we will all be living in closer proximity to each other. There won't be miles and miles of farmland that separates us. We're all going to be living in our urban homes and our neighborhoods next to each other. So more people demanding more power, living closer together with less easy access to land. And when I say land, I'm talking about land that gets you into the urban areas, begs the question, where is all this stuff going to be located? And the obvious answer is in very close proximity to each other. The inescapable conclusion then is if you don't have an ACI problem now, you're probably going to have one soon enough. So I've set the stage and told you what AC and defined what AC interference is. I've also told you that at a macro level, all of the macro factors seem to be indicating that we as pipeline operators are going to have to start playing nice with our friends in the power industry as well. Sooner or later, your pipeline is going to cross with a power line. So you need to be aware of AC interference, how it occurs, and what you can do to mitigate it. So at this point, we're going to take a quick break, and I'm going to send out a poll, and I'm going to ask a question to see how many of you have actually experienced AC interference out there. You don't have to answer now. We'll give you the results towards the end of the presentation out there. Although numbers are coming in pretty quick here, looks like the majority of you actually have experienced AC interference. So you know what it is. I guess you're probably wanting to know how you're going to mitigate this. So we'll get to that soon enough. So with that, how do I close? I'm going to go ahead and close the presentation now, or the poll at the moment. There we go. Okay. And we're going to move on to the next slide. With that, I'm going to hand it over to Mr. Clay Brailsford. Just on an anecdotal story here, I told my young son the other day that I was doing a presentation and we had a good turnout. And my son looked at me and said, "Dad, you're famous." And I said, "No, I'm not famous, son. I'm the opening act for the Rolling Stones." Nobody comes to see me. They all come to see Clay Brailsford. So, ladies and gentlemen, I'm going to give you the Mick Jagger of AC interference, Mr. Clay Brailsford.
Thanks, Andy. I don't think I quite live up to that, but here we go. So continuing with this theme of what is AC interference, and by the way, I'm going to go ahead and give you the end of the story here. The poll was about 80-20, right? So of the folks participating with us today, about 80% of you have experienced some form of AC interference. The other 20% are maybe just interested in this topic. So many of you may be asking, "Hey, I didn't want AC energy on my pipeline. I didn't design it for AC energy. So where exactly is this coming from, and why is it on my pipeline?" So where we normally want to start with your understanding of this is really understand why that energy is on your pipe. And the reason you need to understand the why is because the solutions will involve understanding the why as we go about trying to attack this multi-headed monster that we refer to. So the first area of power transfer exists when the pipeline's under construction. So in the little diagram that we have there for you on the left, what we're trying to simulate is a pipeline that's up on some kind of non-conductive skid, most often wooden skids or maybe even high-density polyethylene. But in any case, that metal pipe is electrically isolated from the ground. So many of you that understand capacitors understand that, well, there's a charged plate and then there's a dielectric in the middle, and then we can induce or capacitively couple or electrostatically couple energy onto the other plate. And that's exactly what we're doing with our pipelines. We don't intend to do that, but that's exactly the condition we've created, where the high voltage AC power lines overhead will electrostatically or capacitively couple energy onto that pipeline. The photograph on the right is just a real life example of that. And then you can see in that particular case that we're exhibiting about 15 volts AC on that piece of pipe. And that's not an unusual occurrence. We'll talk a little bit more about how we mitigate that as we go forward. But right now, we just want to focus on how does this energy show up on my pipeline. So first, capacitive coupling. Secondly, we want to talk about inductive coupling. Well, if capacitive coupling is due to the electric field influence of the electric transmission, then we have to understand there's also a magnetic field influence from that same AC transmission. And that magnetic field influence results in inductive coupling. So what we'll do is we can represent our magnetic field influence with our diagram that you see there on the left. And while those lines of influence are invisible, we're just trying to convey the concept of how that works. So furthering that concept, I want you to think about that inductive coupling as a transformer. So many of us online most often have some experience with transformers in our cathodic protection rectifiers. So much like those transformers, they have a primary side and a secondary side, and those two coils of wire do not physically touch each other. But yet we transform and transfer energy from one coil to the next. The way we do that is through inductive coupling due to the magnetic fields. If you take that same concept and look at what we're doing out in the field with our pipelines and our high voltage AC transmission systems, you quickly realize that, wow, we've actually built a very low efficiency transformer where the primary side is the high voltage AC transmission system overhead, and the low voltage side or secondary side of that transformer is our pipeline. And so with that, you can see that we can transfer that energy onto our pipeline. So we now have our two methods of coupling: capacitive coupling due to electric fields and inductive coupling due to magnetic fields. Finally, we want to talk about the third coupling mechanism, and that's resistive coupling, or sometimes referred to as conductive coupling. This conductive coupling happens because those two infrastructure systems, the high voltage AC infrastructure and the pipeline infrastructure, both share a common denominator. And that common denominator is the earth or the water that both are installed in. So again, as you can see from the diagram on the left, what we're trying to show you is that high voltage AC power system has its own design parameters. And much like our natural gas or crude oil pipeline systems, we design our pipelines to relieve excess pressure or excess volume. We intentionally design that. Our HVAC brothers and sisters do the very same thing. So in the event that they experience an upset in their system, they're going to dump that excess energy to ground. Well, in this case, the ground that they're dumping it to is the same ground that our pipeline's buried in. So when we do that, whether through lightning or through any other AC fault condition that could happen on their system, we can see some of that energy couple onto our pipelines simply because we share that same electrolyte, dirt or water. So there you have it. The three methods of coupling energy onto our pipeline: capacitive coupling, usually evident only during construction; inductive coupling, due to the magnetic fields, that's one that we're going to live with; and then third, resistive or conductive coupling, and that one we also will live with throughout the lifetime of these two structures. So now that you understand where this AC interference or ACI, as we'll tend to refer to that acronym as you look at that, you have to understand that that AC interference condition contributes to risk. So the question becomes, risk to what? Well, first and foremost, we're going to create risk to our personnel. Not only to the pipeline operating personnel, but also the general public, if they have access to our structures. And we're going to use terms like step touch potential, step potential, and we're going to talk about those in the next slide or two. But first, let's identify another area of risk. What about our CP systems? You see the photograph there, and that's actually a magnesium anode ground bed that was terminated in an above ground test station with obviously a connection to the pipeline system. So I want you to imagine that all those mag anodes woke up that morning and they all decided to pull together and really generate a lot of current. And they just generated so much current that they overcame the capacity of that shunt. I don't think any of us would believe that story. What you're looking at is AC energy that was coupled onto the pipeline by any one or some combination of the methods that we've previously described, and it went to ground through those magnesium anodes. So that was AC current that exceeded the capacity of that shunt, resulting in the complete failure of that shunt, actually a catastrophic failure, as you can see from the burn marks. So this goes on a fairly regular occurrence, certainly with our galvanic CP systems. You can also see damage on your impressed current systems much the same way. As cathodic protection professionals, we'll tend to refer to that as lightning damage, but many times that's a misdiagnosis. It might not be lightning, it could simply be inductive current, and we've had some kind of fault event on the HVAC structure, and it can appear as if it was struck by lightning. One of the other areas of risk that we have to think about is the pipeline equipment itself. So here you see the photograph of a gasket, that is a flange gasket that failed during a resistive coupling event. We'll see a little bit more of that in the next slide or two. You'll also hear reports of meter failures, dielectric fitting failure, whether that's tubing fittings, flange insulation gaskets, insulated unions. Again, most often you'll hear that referred to as lightning damage, but as cathodic protection and AC interference professionals, you should be listening for that, as that could be symptomatic of a very general AC interference condition. And then finally, we want to look at damage to the pipeline itself. We can see accelerated corrosion from AC induced corrosion, and this gets a lot of attention in our industry, and deservedly so. But what I want to point out is most often that AC corrosion is only going to happen after some period of time. And all the previous three symptoms are all present long before we see damage to our pipe. So it's only if we're A, observing those conditions and ignoring them, or B, not observing them at all, that we end up with AC corrosion. So the guidance that we're trying to give you today is not only understand a little bit about the science behind AC interference, but also to educate you on the symptoms that you need to be looking for so that you don't end up with that piece of pipe that you see there on the right-hand side of your screen, because you have recognized the symptoms and have taken proactive action to prevent that kind of damage. I mentioned personnel risk, and I mentioned a couple of terms in the previous slide: step-step potential, step-touch potential, and touch-touch potential. And I want to give you some example of what that might look like. So if you take the term step-step potential, by the way, this terminology is all very, very common in the electric transmission industry, not so much so in the pipeline industry. But since we're going to play on both sides of that fence, we have to embrace some of the technology that is used in that electric transmission industry. So when you start looking at risk to people, you have to have some understanding of what happens during a fault event. Just like we have a great understanding of what happens when we hit a relief valve, we really don't want to be looking over the top of that relief pipe, do we? Well, in the electric power industry, you really don't want to be standing close to the epicenter of a fault event, because when that happens and the HVAC system infrastructure dumps that energy to ground, we can create potential lines or gradients that radiate around the point of impact of that event. So much like a rock hitting a pond, you can have these gradient lines that radiate away from the point of entry of current into the ground. Many of us are familiar with the term IR drop from our CP world. If you take that same concept and think about AC current flowing through the ground, and you imagine that the ground has some resistance, we now have current flowing through a resistance, which results in a voltage drop. And that voltage gradient or voltage drop can be really, really steep, as you can see from the little diagram there on the right. So it's not unusual to see thousands of volts in a fairly short space, thousands of volts difference in a relatively short space. So as you look at our little depiction of two footsteps, you can see that it would not be unusual to see 5,000 volts difference just between your left foot and your right foot. I don't think any of us would intentionally put our feet across a potential difference if I told you that there's 5,000 volt difference between these two gradient lines. Please step there and let's see what happens. I don't think any one of us would willingly do that, but yet that's what happens if you're around one of these events when it occurs. So that first example of risk, where we talk about risk to people, is through these kinds of events: step potential, step touch. When we talk about step touch, what we're referring to is, in pipeline lingo, if we're greasing a valve, or more commonly, if we're a corrosion technician, what if we're out there taking a pipe to soil potential? You can quickly understand that we're touching the pipeline. If that pipeline were to suddenly move in AC voltage from something near zero to several hundred volts or even thousands of volts because of an AC upset event or a lightning strike, you can quickly see that the potential where your hand is touching the pipe and your feet is going to match that same voltage difference. As soon as there's a voltage difference, current will flow. In this case, it's going to flow through your body, and that can result in a catastrophic event. The same thing can happen with touch potentials. If you happen to have your hands across an insulated device, whether that's a flange insulation kit, a dielectric, any kind of dielectric fitting. So with that, I hope you have a better understanding of this terminology and where AC interference can result in personnel risk, primarily through these different potentials. If you think, well, Clay, that's all well and good, and I understand the concept, but does that really ever happen? And I think I would challenge you to think back what you've heard and maybe what you've even read of lightning strikes, AC fault events that can happen. Most often it results in livestock kills and things like that. Every now and then we hear about catastrophic events that happen on golf courses, maybe even a football team that's practicing in those late fall days, and we get those late summer thunderstorms with a lot of lightning. And we hear stories about the football team was struck by lightning. I'm here to tell you that lightning did not come down from the sky and strike those individuals at the top of their helmet. Lightning most often struck a chain link fence nearby, or more often, even a steel goalpost, and went to ground, created gradient lines that subjected some of those individuals to a potential gradient, and they felt that current flowed through their body and they fell over. So these are well-documented incidents that can happen. They can happen around our pipeline facilities just as easily. One could make the argument that, well, that doesn't happen today. Why will it happen more if I have a co-location with a power structure? Well, the answer is, as soon as you co-locate with an HVAC structure, you're going to be more susceptible to any upsets on their system because they happen. Just like we have overpressure events on our pipeline systems and we vent that to the atmosphere, you have to understand that the electric transmission system also has upsets on their system. They're opening breakers, closing breakers. They're experiencing upsets in their system during lightning storms and thunderstorms. So all of these things are going on their system each and every day, 24 hours a day, 365 days a year. As soon as we co-locate with that, remember that conductive coupling or resistive coupling that we talked about earlier. We as pipeline operators are going to feel the effects of that. It's incumbent upon us to recognize, number one, the science behind what's happening, and then number two, understand the risk that's inherent to our pipeline operating personnel, the general public. Number three, the risk to our pipeline equipment. And then finally, even a risk to the pipeline itself through AC corrosion. One of the ways that you would look to mitigate that would be to create an even plane or create a gradient such that the potential differences would be minimized. So we talk about gradient control, and we try to create that around our pipeline systems so that, in effect, we as certainly pipeline operating personnel, but even the general public, could be in close proximity to that pipe or even touching that pipe. In the event an upset occurs, we would simply look like a bird on a wire. Both feet are at the same potential, so there's zero potential difference, no current flows. So that's the concept behind gradient control. And we'll talk a little bit more about that as we talk about mitigation methods. Remember, we're still talking about resistive coupling. I have some photographs here that were shared with me by an operator that experienced a flange insulation gasket failure. In this case, he received a phone call that he had a meter run that was on fire. That's not a phone call any of us want to receive. Upon responding to that event, he did indeed find that his meter run was on fire, and he could identify the source as a particular flange set. He was able to shut the gas supply off, get the fire under control, and then upon investigating that event, he found that this particular well pad that he was responsible for was served by an underground electric power system. This particular landowner did not want any overhead structures on his property, so they had transitioned from an overhead power supply to an underground power supply. At that point, they had set an above ground transformer, just a pad mounted transformer many of us are familiar with. And so the picture that you see there is what he sent me of what that transformer looked like. So all of us can tell that something bad has happened here. There was obviously a lot of heat generated. So as we opened the transformer, this is what he saw inside. You can see there's 3 terminals there. Those represent the 3 phases that we should have seen. One of them is gone. This is the gasket that he removed from that meter run. So you can see the damage there at the 6 o'clock position. You can also see the blackened material there where the ensuing fire was evident. And then finally, we excavated the pipeline adjacent to the transformer because, again, remember, that's where the event started. So that's where the rock hit the pond. The greatest gradients were present adjacent to that transformer. As the pipeline was about 3 to 4 feet away from that transformer, you can see the black marks there on that pipeline. I could tell you that was pitting on the pipe, but that would be incorrect. This particular pipeline was covered with rock shield, high-density polyethylene mesh, and but the heat that was generated from the arcing melted the rock shield onto the pipe. When he did remove that, we did see evidence of some wall loss on the pipe, but on the order of less than 10 mils of wall loss associated with that event. You heard Andy mention some of the markers that are important in this identification of AC interference. So as we start moving into other symptoms that you want to look at, as we start dealing with induced AC due to those electromagnetic fields, this is the event that most of us are going to live with on a continuing basis. Fortunately, we do have some guidelines to help us as we assess our patient. If you think of our pipeline as a patient and you're the doctor, if you want to look at some guidelines for could I be at risk, we would recommend that you refer to the AC current density. So you can see there on the left what we might call the stoplight or the traffic signal indication. If those current densities are less than 20 amps per square meter, you're probably okay. If there's something between 20 and 100, we're not so sure. You need to keep an eye on it. And certainly if they're greater than 100 amps per square meter, you're going to expect an AC corrosion problem and need to monitor that very closely and most often take mitigation measures. In our new NACE standard, you'll see references to a combination of both AC and DC current density, and we've listed those here for you as well. Another way that we look at this data is through what we refer to as the Prinze Diagram. What we're referencing here on the vertical scale is AC voltage. On the horizontal scale is resistivity. Both of these are logarithmic scales. And then we've overlaid those same green, yellow, and red lines to make it easy for you to visualize those levels of risk. Now, the point here is there's a relationship between AC voltage and soil resistivity. Many of us are familiar with the safety standard of 15 volts that we see on our pipelines. So we've been taught through the years that if we have 15 volts AC or less, we do not have a problem. It's important that you understand that is a safety standard only. And we represent that with that shock hazard limit, that dashed purple line that you can see there on the graph. However, if you're in lower resistivity soils, you can easily experience AC current densities of 100 amps per square meter or even greater at voltages much, much less than 15 volts. So the point here is the AC corrosion risk can happen at voltages much less than 15 volts, which is the established shock hazard limit voltage. So please be aware of that and understand that all of these things contribute to this multi-headed monster that we're trying to do battle with. When we talk about AC corrosion, it's important that you understand what you're looking at if you're involved in a pipeline excavation or an open ditch excavation. What we're trying to show you with the first photograph there, the white that you see at the top of that photograph is an extruded coating on this particular pipeline. You can see that coating is deformed at roughly the 6 o'clock position. When looking at that photograph, you'll hear that described as a volcano or even a gunshot wound. But that's generally what you're going to see. So you should be aware of that and be actively looking for that in any open ditch or pipeline excavation where you suspect AC interference. The second thing that you might find is the tubercle. The tubercle is a hard deposit that you'll find attached to the pipeline. It's not always going to be there. It's dependent on the composition of the soil, but many times you will find that hard tubercle present as well. Obviously, you're going to have to get there early in the excavation process to be able to find that. And then finally, the morphology of AC corrosion itself on the pipe usually will be described as pits within pits. They're fairly rounded in shape. Many people might confuse that with microbiologically induced corrosion or MIC. So in and of itself, if you just see the one photograph there on the right, you would have to say, this could be AC corrosion or this could be MIC. It's only when you gather additional information and find out more about that particular situation that you can make an accurate determination of a most probable cause of corrosion. Our AC risk factors will be controlled by design conditions, and those are design conditions associated with both the pipeline and the HVAC system. Our CP system design will have some impact on that, whether we're using galvanic anodes or impressed current systems, and then certainly our environmental conditions will have an impact. We'll be expounding on these in later sessions in some more detail. That risk is going to vary with the operating conditions. So it's not simply what the pipeline and or the HVAC system was designed to operate at, it's also how it's actually operating, both the pipeline and the HVAC system. Our risk is very, very different with a pipeline in construction, i.e., we're much more concerned about capacitive coupling when a pipeline's in construction. Remember, that's when our pipeline's up on the wooden skids, than we are about inductive coupling. Once the pipeline goes into service, that risk transfers, or that mechanism transfers to inductive coupling and resistive coupling. So again, the science behind the energy coupling is very, very important to how it's actually going to manifest itself on your pipeline. The same applies to our HVAC systems. We can have, as you talk about terminology on the power transmission side of the world, you're going to hear terms like normal operations. You'll hear about fault conditions, short conditions. You have to learn to differentiate between what is a 60 hertz event and what is a non-60 hertz event in other words, lightning. Our Code of Federal Regulations will give us some guidance. 49 CFR 192 and 195 both direct us to this particular phenomenon. Unfortunately, they don't tell us how to fix it. They only tell us that if you have these conditions, you need to do something. If we turn to NACE, we see a number of references there. Our newest standard, SP 21424-2018, addresses AC corrosion, and that is an extremely important document. If you're experiencing AC interference, I would highly encourage you to reference that document. Our safety document, SPO 177, was recently updated, and that addresses the safety concerns associated with AC energy on our pipeline systems. There's other documents that we reference here for you that could be very useful in your exploration of this topic. Other industry standards and reports include Canadian standards, European standards, INGAA that Andy mentioned previously, even the National Electric Code and PRCI weigh in on this subject. So as we bring this to a close, we have a couple of questions here for you, and we're just going to talk through these. Hopefully you could answer this correctly. Which of the following is not a type of AC interference? Well, answer one, capacitive coupling. That makes perfect sense. That's actually the first one we talked about. Derivative coupling, answer number two. I'm not even sure what that is. Number three, inductive coupling makes perfect sense. And number four, resistive coupling, that also makes perfect sense. So I think I would decide that number two is not a type of AC interference. Look at that. How about that? According to INGAA, how many amps per square meter would indicate a high risk of ACI corrosion? 10 amps per square meter, 123 amps per square meter, or 76 amps per square meter. Hopefully you all recognize the limit of 100 amps per square meter, so obviously number two would be the correct answer here. And finally, review question number three. Step potential is defined as the voltage that can exist in the earth within the span of one step, with each foot referenced to a different voltage. That sounds good to me. I'm going to vote for true, and there we are. So with this, hopefully you're seeing where we're going. If you can identify that you have an AC interference issue, what can I do? We can talk about computer-based numerical monitoring, engineered field design, and those will both be topics for future sessions as we continue this webinar series. So with that, I'm going to turn it back over to Andy to wrap us up for the day and hopefully answer any questions that might have come in.
All right, Clay, thanks for your time. Obviously, dynamic, elusive, multi-headed problem. You're going to need some expertise and some help to mitigate and tame this guy, tame this monster. So let's look at see if anybody submitted any questions. We did have some here. Now let's see. If you're talking, we can't hear anything. Goodness. Well, hopefully that problem was resolved. And you guys were able to hear us. Next question was that we came in was, what about my close interval surveys? As I do my close interval surveys in a co-located area, does AC interference affect my close interval survey results?
So this is Clay. My answer to that would be absolutely. First and foremost, understand there's a tremendous risk to the people conducting that survey. If you can imagine, most close interval surveys are conducted with a big coil of wire. And so we're going to put that on our back or put it on our hip. Well, if you understand the science of energy coupling, you can understand that AC energy is most likely going to be coupled onto that roll of wire. It's going to look like a very large inductor, and you're going to expose your personnel to severe AC shock hazard when you do that. Secondly, as you string that wire out under the power line, that same induction effect is going to be present on the wire. And so most often, using normal close interval survey standards, you're simply going to be reading the AC voltage that's induced on your test wire. It will have little or nothing to do with the AC voltage on your pipeline. So if you're committed to running an AC interference or an AC close interval survey, you need to consider alternate methods, i.e. shielded cables and other ways that you can minimize the induction effects of the AC on your wire.
We're running out of time right now. So we did have a couple of more questions that were submitted, but I'm sorry, we've run out of time here. So we're going to move on. If you do have those questions, I think we have your contact information. We'll try to respond to you via email. I apologize, we're not going to have time to answer your questions right here. So we're going to wrap it up real quick. Today was part 1 of the 4-part series, AC Interference 101. We'll come back in about 2 weeks. We've defined the problem. Hopefully you're aware of the phenomenon and the potential for threat on to your pipeline and your assets and your people. So our next session is going to be focused on what can you do to mitigate? What can you do to tame or control this multi-headed monster? So join us next week, June 19th, again at 10 a.m. Central Time for part 2. There. So you've done part 1. Also, Anna, correct me if I'm wrong, we'll be sending out a link to where you can download a educational credit, 1 hour of educational credit for those of you who want to put this into your professional development portfolio. You should be getting a link from Anna with where you can download that. So join us join us in 2 weeks. And by the way, if you join us for all 4 sessions, we'll send you a AI or BAS logo cap. If you haven't seen the AI and BAS caps, they're pretty cool. So be sure and join us for all 4 to get your baseball cap. With that, we're going to wrap it up. Again, apologize, couldn't answer all the questions. We'll try to respond to your emails a little bit later, or your questions via email a bit later. So thank you all. Thank you for your time, and good luck out there. Be safe.